Michael Moreau. He's a flight dynamics system manager, and he's a native of Vermont. While he was in Vermont, he became a NASA Academy intern at Goddard, and that brought him close to Goddard. From there, he went to University of Colorado and got his PhD in aerospace engineering. Mike's had many awards, but specifically, he got the Robert H. Goddard Leadership Award, as well as the Honor Engineering Award from Goddard. He got the NASA Outstanding Leadership Medal in 2017. The Tycho Brahe Award from the Institute of Navigation. And if you remember, back in August, we had Alice Bowman speaking to us about New Horizons. And Alice Bowman has an asteroid named after her. Well, I thought that was it. Well, it turns out Mike Moreau also has an asteroid named after him. Sounds like an elite group of people with asteroid, and I hope you track it every day. And I want to thank Carl Staley for recommending that we bring in Mike to talk about returning a sample from asteroid Bennu. Mike.
I'll try to speak up too. Can you hear me now? How's that? Oh, a little too much? Test 1, 2, 3. Test 1, 2. Thank you, Arlen. Well, thank you for that nice introduction. Actually, everybody that worked on the OSIRIS-REx mission has an asteroid named after them. It was a very special honor that was bestowed on the team around the time of launch, and it was because Ed Bayshore, who's the deputy PI for the mission, was the lead of the Cali Sky Survey. And the way that you get to name an asteroid is if you discovered it, you get to name it. Well, Ed developed this software that allowed hundreds of thousands of Near Earth asteroids to be discovered, tens of thousands anyway. And so he had naming rights to hand out, and they thought that that would be a really nice special recognition for the team members that worked so hard to get the mission ready for launch. And, so that's why I also have that asteroid. So I wanted to talk a little bit, too, about how I've been at Goddard since 1994. That was when I first came there as a summer intern. So it's really nice to see some familiar faces that I've seen around Goddard and also some people that I knew here today. But I don't know if any of you remember Jerry Soffin. He's the person who was responsible for bringing me to Goddard and started this summer internship program. That was really unique and probably would not have gotten this farm boy from Vermont to come to Goddard or find his way to Goddard without Jerry. So. Anyway, OSIRIS-REx is a really amazing mission. I don't think people realized quite how special this mission would be when it was first envisioned. It was just such a wonderful feather in Goddard's cap to have been responsible for leading this mission. And I see John Albright there, who was one of the people who worked in 2000s to try to win this mission for Goddard. So many years. That's when this mission started. It was originally put forward as a discovery proposal in around the 2007 timeframe. But even before that, the University of Arizona and Goddard were working on this mission. It wasn't selected until 2011. And then as a New Frontiers mission, that's a larger budget. And it turned out to be very important to have that budget because the scope of this mission was very challenging and more challenging than anybody expected. Let's see if I can get this to you. Maybe that it's forgotten that it was connected here at one point.
You turn it on?
Yeah, just power cycle it. So let's start by talking about Bennu. Bennu is a near Earth asteroid, so this shows you a little diagram of Bennu's orbit with respect to the Earth.
There's an on-off switch.
So the Earth's orbit's here in green, Bennu's orbit is in blue, so it's very similar. It's in the same part of the solar system. It's slightly inclined relative to the solar system, and it also has this intersection point in September of every year with the Earth's orbit. That's what makes Bennu particularly interesting. It's one of the most hazardous asteroids that we know about, and that's because of its intersection point with the Earth's atmosphere that happens, or the Earth's orbit that happens every year. It also makes it a great asteroid to send a sample return mission to, because from a trajectory design standpoint, you need to find a target that you can not only get the spacecraft to, but also get it home within a reasonable amount of time. And that's, 10 years or something is what you're talking about from a trajectory design standpoint. So time and fuel, Bennu was a great target for this mission. So the imagery that you're seeing on the screen is radar imagery that was made from the Arecibo. Oh, so no blocking the screen. Yeah, sure. So this imagery is from the Arecibo Observatory. It's basically the data that we had about Bennu before the mission launched. And this shape here is from radar data. Is actually very close to the gross shape of Bennu, and the spin rate and all of those things turned out to be very, very similar to what we were expecting. However, when we first saw Bennu up close, that's when we got our first surprise, and we knew we were going to have some problems. So this surface is completely covered in rocks. Some of these rocks are the size of a 3-story building, and some of them are the size of a car, the ones that you see all around here. But the problem is, we thought Bennu was largely a smooth, sandy beach, and that was based on thermal imaging data that was derived from radar observations. It was very uniform, meaning it was probably all the same kind of material, the same morphologies of materials. When we got there, we realized it was completely different, completely covered in boulders. And what that meant was that the spacecraft had been designed assuming there was some space on the surface that was at least 50 meters in diameter that was clear of obstacles. And there's no places like that on Bennu. So immediately we knew that the whole navigation system that we had designed using LiDAR to target the spacecraft down to the surface wasn't precise enough to land safely on Bennu. So we kind of went back to the drawing board around several aspects of the mission at that point. Okay. So we did spend about 2 years orbiting and studying Bennu up close. The timeline of those observations are shown at the bottom. But what you're seeing playing out on the screen is the track of all of the orbital trajectories that we flew as the spacecraft operated around Bennu. So we started out by doing a slow approach, and we did some flybys to sense the gravity of Bennu more precisely. Then we got into orbit for the first time. Now what you're seeing is a series of detailed survey flybys. So we flew by the asteroid at different solar phase angles and distances to do a precise global map. And then once that was completed, we got back into an even lower orbit to do global mapping as well. So this first orbit we were in was only 2 kilometers from the surface of Bennu. The second orbit was a radius of 1 kilometer, so we were only about 600 meters from the surface. The spacecraft, when it's orbiting Bennu, is moving at just about 10 centimeters per second. So in order to change the orbits, all of these little inflection points that you see in these trajectories are thruster firings that change the velocity somewhere between 2 and 12 centimeters per second. It's really a dance. It's not a traditional orbiting mission where you do a big burn and get captured into orbit. This was like a dance. It was a proximity operations campaign. So as this is playing out, you're seeing all the things we did, including getting ready for the sample collection. The most challenging thing we did was these close reconnaissance passes. So we flew within about 200 meters of the surface to get up-close observations of the sample sites. And, Bennu was covered in rocks, so we had to figure out where are we going to collect the sample. There were no great places, and that caused us to have to change up the observations. We had to do these reconnaissance passes at a larger number of areas to try to just figure out what was the safest site. What sites didn't have hazards, which sites had material that could be injected into our sample mechanism, which is already designed on the spacecraft. So the reconnaissance and all of that stuff that we did was very critical to that. I want to talk about how we collected this sample from Bennu. It was an innovative design called Touch and Go, which is just what it sounds like. It's kind of like the spacecraft was on a pogo stick. So it extended this robotic arm here, which is extended this robotic arm, which is about 2 meters in length. It has a little sample collection mechanism on the end. It's about 30 centimeters in diameter, so about this big. And you can see how the sample collection mechanism works in this video here. So the spacecraft is navigated down to the surface. It just makes contact with the surface, and then there's high pressure nitrogen gas fires. It just stays in contact for a few seconds, long enough to drive material up into the sample collector head, and then the thrusters fire and back away. So that whole sequence involved touching the surface for maybe 15 seconds. And I'll show you a lot more about how all that played out. So the other part about TAG was the trajectory that we flew. We started out in orbit around, let me start this one over again actually. We started out in an orbit around Bennu that was that 1 kilometer safe home orbit. And we had to phase the spacecraft to get it to just the right position to start the TAG maneuver. And that involved doing maneuvers that were about 1 to 2 millimeters per second to get the spacecraft to arrive at the right place in the orbit to start the TAG. Then the spacecraft flew out over the front side of the asteroid for 4 hours, and then it got to the point where it did this checkpoint maneuver at about 150 meters altitude. The checkpoint basically started it on the descent to the surface. Then it did this second maneuver called match point. Match point was designed to get the spacecraft to match the rotation of the asteroid and get at just the right spot at just the right velocity. Then the spacecraft descended into the TAG site, touched down on the surface. Once contact was detected, gas bottle fires and collects the sample. So this is how we designed TAG to work. This was the intention of how TAG would work. But I mentioned the fact that we didn't have any places that were 50 meters in diameter. So we had to come up with some new capabilities for the spacecraft. This just helps you visualize the size of the sample. Basically, there's a yellow circle here that shows you the area that the spacecraft was designed to target. So it's supposed to land somewhere within that yellow ellipse. This blue ellipse is about 8 meters. And that's basically the best site that we found on Bennu was about 8 meters in diameter as opposed to 50. And it just gives you an idea of the scale. Here you can see the cars. We're basically targeting landing in an area that was the width of a few parking spaces. And right next to it, there were large boulders that were the size of a 2-story building. So it's kind of like parking the spacecraft in front of the garage at your house if you have like a 3-car garage, and not hitting the house on the way out when you take off. So that was the challenge that we faced. And so the response to that was, number one, we had a backup navigation capability for TAG that used cameras instead of a LiDAR. And the optical navigation is used throughout the entire mission. That's how we do the relative navigation relative to Bennu to the precision that we need to do these millimeter and centimeter maneuvers. But natural feature tracking was basically taking that pieces of that OpNav capability, putting it on the spacecraft and letting it do it autonomously. So we built these maps, loaded them on the spacecraft. The camera autonomously took pictures and compared the pictures to the data in the maps, found a match, and then would be able to compute an error in its trajectory based on how far the map was off from the images that were taken. So that technique was used during TAG to navigate down to precision that was more like 8 meters instead of 50 meters. The other problem that we had was that even within the site that we selected, there were objects that were large enough to be a hazard to the spacecraft. Things bigger than this podium, size of a car. If the spacecraft were to come down on that object, it could damage the spacecraft and cause us to fail in the sample collection. So we also built a flight software patch that wasn't envisioned, where we took that map data. So we had really great topographic map data, allowed us to figure out where are the green areas where it's safe to touch, where are the red areas where it's not safe to touch. And that was loaded on the spacecraft, and then it took the positional information that was computing in real time. And if you were computed to land in one of these green spots, it would let you go. if you're coming down on the spot that was red, it would fire an abort at 5 meters and keep the spacecraft safe. So all of this work was done between arriving at the asteroid basically in January 2019 and when we're ready to do the tag in the summer of 2020, about 18 months. And all of these changes were implemented and really showed great response of the team to be able to do that. So now I'm going to show you some of the data from the actual sample collection. On the left, you're seeing video from the SAM cam, and this is showing the robot arm in the field of view. As it touches the surface, fires the gas bottle, and then you can see kind of chaos erupts in imagery as material just goes everywhere. This image here is the wide field of view navigation camera. It's pointed off to the side, so it's showing you a different field of view and a wider field of view. And as this plays, and the spacecraft, I'll take you through what's happening as this recycles, but you're seeing right here the shadow of the arm backing away. This is as the spacecraft is leaving the surface. And this is a big plume of debris that was ejected from the contact over here. And here's a trough that was excavated by the thrusters that were firing. So the thrusters cleared out all of this debris in this area right here. And you can see this whole cloud of debris moving away. There's a shadow being projected on the original surface here. So anyway, a very dramatic effect when we touched the asteroid. In fact, more dramatic than we were expecting. The surface of Bennu was very, very loosely held together. It was like touching in a ball pit. If we had not fired the thrusters, the spacecraft would have just been enveloped by that surface. So I have a little close-up view here that just shows you a little bit about what's going on. So this is a frame that's just before contact and just after contact. And you can see there's a couple different morphologies of material on the surface. This looks like a rock right here at 12 o'clock, but as soon as we touched it, it kind of just disintegrated into dust. So that was one morphology. Here you're seeing a boulder that has some structure and is kind of cantilevered up as the spacecraft pushes on it. So there was a mixture of different materials there. And this sequence of images here is what's happening after the gas bottle fires. And basically the timeline of events is we contacted the surface, we fired the gas bottle about a second later, we continued descending about 1/2 meter into the surface before the thrusters fired, and then we started to back away. And we rose above the original surface about 16 seconds after we touched. So after we did the tag, we went back and took some additional observations to see the change that we had made, and that's visualized here. So basically we excavated a crater that was about 1/2 meter deep and about 6 meters wide by 3 meters wide. Several tons of material was moved by the combination of the gas bottle and the thrusters firing and pushing that material out. So this was really, really surprising. That in combination with how loosely held together the surface was, we barely triggered the accelerometer threshold to fire the gas bottle. It would just barely met that threshold where the gas bottle would fire because the resistance from the surface was just so small. The good news is, however, we collected a really significant amount of sample. Bennu was not done surprising us, though. We had planned to move the arm out in front of the camera and take pictures to verify that we had a full head of sample. Well, what we saw was material escaping from the head. And basically some of the material was in probably larger rocks were jamming this little mylar flap open that was supposed to let material go in and then close. So the head was so full of material that it was partially held open. What that meant was every time we moved the arm, it was shaking material out like a salt shaker. So we went to all this work to collect the sample, and we were rapidly losing it. So we went into a contingency mode at this point and stopped all the planned operations on the spacecraft and slews so that we wouldn't lose any more sample, and we rapidly executed the stow. So we had to get the approval at the senior level of NASA headquarters for the stow decision, but we had to do that rapidly and make the decision to stow because once it was irreversible. Once you put the head in there and cut the bolt off, you can't try it again. So we put the evidence together to suggest that we had enough sample, and the safest thing was just to get it stowed, and we did that. And then we had to wait and see what the result was. So that was in October of 2020. We did this snow operation. Then we did the re-imaging of the tag site in the March, April 2021 timeframe. And then May of 2021, we did a maneuver to leave Bennu. That image you just saw was the last polycam image, last image that we recorded of Bennu. So we did a main engine burn in May of 2021 that set us on a course to intercept the Earth in September of 2023. And we just had to do a couple of minor cleanup burns to execute that. This shows the trajectory of the spacecraft on its way back to Earth with the rendezvous. It shows you the capsule being released by the spacecraft, and then an animation of what we thought it would look like as the spacecraft entered the Earth's atmosphere, recapsulating, and then it's landing in a place in Utah called the Utah Test and Training Range, where we would go out and cover it with helicopters and then transport it to the Johnson Space Center. And I've got a lot of pictures and things that I can show you about that landing that executed. So on the first part of the mission, I was responsible for leading the navigation team and the mission operations. Over the last 2 years, I've been responsible for leading the recovery team and the recovery planning for the capsule. So I'm going to talk a little bit more about that now. So in order for us to deliver this capsule back to Earth, we want to put the whole spaceflight system on an intercept trajectory to Earth. But we then release the capsule and fire a burn on the spacecraft so the spacecraft will divert and miss the Earth. So that sequence starts in July when we did a final trim maneuver. That set us up on a trajectory that would fly by the Earth at about 125 miles distant. On September 10th, that was 2 weeks before landing, we did a maneuver that basically moved the aim point of the mission from 125 miles off to intersecting the atmosphere off the coast of California. And that was the intercept point that would allow us to land in Utah. A week later, on September 17th, we did another burn to just clean that up to get right on target. And then the capsule was released on September 24th around 4 a.m. Mountain Time, and the spacecraft diverted about 20 minutes later. So the capsule actually released about a third of the distance to the moon, 100,000 kilometers from the Earth, and then it just coasts for 4 hours. So that just blew my mind when I really thought about it. You know, that it's a spring mechanism. It gets a little spin and a release at about 40 centimeters per second, but the fact that we can design it to just go that whole distance without any correction and land in the right place just kind of blows my mind. And just is a testament to the job that the navigators and the spacecraft operators do to get that right. So if that all goes well, 4 hours after release, the capsule enters the Earth's atmosphere. It would be at 8:42 a.m. Mountain Time on the 24th. About a minute later, it's already at its peak heating and peak deceleration milestones, and then within about 2 minutes, 2.5 minutes, there's supposed to be a drogue chute that deploys. It rides in the drogue chute for maybe 4 minutes, and then the main parachute comes out and it descends down into the landing area. It's supposed to land at about 10 miles per hour. So this is the area that we were targeting for the landing. We picked this area in Utah. It's called the Utah Test and Training Range. It's also in the vicinity of the Dugway Proving Grounds. And there were actually 2 different branches of the DoD that we worked with, the Army on the Dugway side and the Air Force on the UTTR side. They share the range out there. But it's about an hour and a half west of Salt Lake City, Utah. It's really in the middle of nowhere. The landing ellipse was in the middle of the training range, and our teams were, all the operations and the facilities we had were about 30 miles away from the landing site, so it's pretty remote. We're talking about large distances. The ellipse itself was something like 14 by 60 kilometers. That was the landing footprint on the ground where we expected to be. This just shows you the restricted airspace of the GTR. So that was kind of our safe landing area, more or less, and this is the actual footprint that we expected to come down in. So this place is very remote. It's also very beautiful. I don't know if anybody has ever visited the Great Sand Dunes National Park in the St. Louis Valley of Colorado, but it's very similar to that. There's very big relief with these huge mountains, but also like a flat, dry lake bed type area. So this was taken by one of the NASA photographers, a time-lapse photo, one of the mornings that we did our dress rehearsal in August. That gives you an idea of the wide open kind of remoteness of the area. I remember on landing day at about 5 a.m. When I arrived at the facility, very clear sky, and I can clearly see Mercury and Venus above the horizon just before sunrise. And it's very hard to see Mercury. It's just the right conditions, but it was beautiful and just so clear as day. And that was a big memory that I had of that. So this is imagery from the navigation camera. I'll try to use this one instead.
Yeah, I'll turn that one.
Can you hear me through this one? Yes. Okay, so this is imagery that was taken from the navigation camera on the spacecraft, and it's situated so that when the capsule is released, you can see the capsule departing the spacecraft. It's not the best photos because the sun was only about 30 degrees off the camera bore site. So what you're seeing in the picture here is this is the Earth, just a sliver of the limb of the Earth, and the capsule will enter the field of view up here. So you'll see the capsule right here, departing the spacecraft. So this is, as I said, about a third of the distance from the moon. We didn't get this imagery down until the next day, so we didn't actually have this confirmation in real time. The only confirmation we had of the release was we saw a small Doppler shift in the radio signal from the spacecraft. That was the force of the capsule leaving. But that's how good the navigators are, that they could see that change. That was our main confirmation of the release. So our first indication that things were going to be okay was this infrared camera that's on a WB-57 aircraft. This aircraft is flying at about 50,000 feet altitude. You can see the capsule right there in the field of view of the IR camera, and then they zoom in, and you can see this little streak, the fireball. This is about 30 seconds after atmospheric interface. So it was right on time. We started to see this, and this was played live on NASA TV. So we were very excited to see this. That previous view was an infrared camera. This is actually the color camera on the same aircraft. So again, this aircraft is flying at about 48,000 feet, and it has a camera in the nose that's tracking the capsule based on the predicted location that we gave it. So this is perhaps a minute after entry interface, right around the time that the capsule is going through its peak heating. And then within another 30 seconds or so after this, it's going through its peak deceleration, which is about 30 times the acceleration due to gravity. So what we would have expected to happen next is that the drogue chutes would have deployed in about 2 minutes 15 seconds to 2 minutes 30 seconds. But unfortunately, that did not happen. So this is about 3 minutes after entry interface. And you can see the capsule here. It's still being tracked by the WB-57. It's now lower in altitude, which is why you see ground going underneath. You see features and geography. If you can zoom in on this, you can see the capsule is actually tumbling. The purpose of that drogue chute is to keep the capsule from tumbling so it has a stable flight when it gets into this subsonic regime. So luckily the sensor that triggers the main parachute deploy did work as planned, and all of the parachutes, including the main parachute, you'll see come out all at once here in about the next 20 seconds. And then you can see it's there on the main parachute. So this is about 5 minutes after entry interface. 42, yeah, this is about 5 minutes to 6 minutes after entry interface. This is actually earlier timeline than what we expected because the drogue didn't come out and slow it down. So it was moving towards the ground faster than expected. And then the whole landing was about 3 minutes early. So NASA's been looking at this since the parachute deployment sequence didn't go as planned. Our contractors are looking very closely at this to try to understand exactly what happened, and we think we understand it pretty well right now, and we're actually working on preparing to communicate that out to the community. But the bottom line is that the parachute, there was enough margin in the design of the main parachute system that even though it was moving faster than it was intended and it wasn't in a stable flight, it was still able to stabilize and deploy and land successfully. So I won't let this play because it takes like another 5 minutes to track it all the way to the ground, but we have great imagery from 2 or 3 different cameras that we can use to reconstruct the trajectory and everything that happened. So I'll just let this play, but it shows you some of the sequence events of the recovery. It took us about 10 minutes to locate the capsule on the ground. We had 4 different helicopters that were out there. This video that you're seeing right now was by the second of the 4 helicopters. Just doing aerial footage. You can see the parachute right here. This is our on-scene commander, Stu Wiley. He's doing an unexploded ordnance check. This is the bombing range. The very first thing that we need to do is check and make sure there's nothing dangerous around the capsule that our team would be operating around. And this is Vicki, who works for Lockheed Martin, and she was going up to make sure there wasn't any toxic gas coming from the capsule, because there was a battery inside, and if it was complicated, then that would be a problem. It took them about 45 minutes to do all the procedures with the capsule, and then they put it up in this netting, wrapped it up, put it in this netting. It was carried by a long line, the 30-mile trip back to the hangar in the base area where our team was operating. We had a temporary clean room facility set up there because one of the most important things about returning the sample from space is to keep it pristine. We don't want to get the sample in the lab and see evidence of the Utah desert, right? So that was part of the reason for using the helicopters, having a rapid time-fine recovery, and then we had a clean room that was set up in a hangar at the UTTR where the capsule was brought into to disassemble and prepare for shipping to Houston. So before we brought it into the hangar, we did another check for any kind of leakage of toxic gas from the batteries. Once that's okay, we wheeled it into the clean room, and then they did some disassembly steps. They took off the back shell, removed the sample canister, so the sample head is actually enclosed in another canister. That is what got shipped to Houston, and we went from there. And I don't know how many of you were able to watch the coverage of this on live. It was played on NASA TV Live. Yeah, great. So these are some snapshots of the next day when the sample was transported to the Johnson Space Center. We flew on a C-17, which allowed us to carry the sample canister and the nitrogen gas purge equipment, and also a number of the key team members that had to be there for the processing of the sample in Houston. So this is one of my favorite pictures. That's me and Richard Witherspoon, who's the Lockheed Martin recovery manager. Now that our job is complete and the sample was bolted down into the cargo bay of the C-17. We flew that morning to Houston. You can see here, this is the caravan of the canister and the nitrogen purge system being wheeled into the purification facility at Johnson Space Center. It's the same group there that curates other astromaterials, including all the lunar ring rocks that were returned during the Apollo program. The final responsibility for me as the NASA Goddard manager of the mission was the opening of the sample canister. So this is the canister head, this is the tag SAM, and once that was lifting that off was the last step where we hand off to the Johnson Space Center to be responsible now for the hardware and for the sample. And this is the picture of how we ended that first day in Houston. And this is a close-up, so you can see the tag SAM head here in its capture ring. And this was our first look at Bennu. All this material that's scattered around the deck came out of the head, during the ride to the ground. And you can see the lid here is coated in some of the sample material. There's material on the top of the head. And you can see this, there's like a braid line here where the seal of the canister was, where the material got pushed up against. So just that material was the first sample that we had to look at. And then very shortly thereafter, we removed the tag SAM head from that fixture, flipped it over, and we could see a bunch of material that was here sitting on the outside of the flap. So this isn't even the inside of the head yet. This is just the material that's kind of falling out. And this is the zoom in here. And so the team was able to collect all of this material and also collect a bunch of stuff. You can see some little bits and pieces here holding the flap open. They were able to collect over 70 grams of sample just in this configuration. And our requirement, by the way, was 60 grams. That was what we were shooting for to bring back. We think that there's about twice that amount in total in the head. But just to show you that things don't always go as planned, in order to open the tag sim, you have to remove this base plate. You see all these little thick screws here? Well, they were able to get all of them out except for two. And then the tools that they had approved for use in the clean hoods where they're working yielded, and then they had to stop. And so they have then taken the 70 grams that has come out, they're distributing that to the science teams, and they're coming up with a backup plan to try to get the last two screws out. So what are we doing with this sample? I'm not a scientist on the mission, I'm an engineer, but I know just enough to be dangerous about the key science. But one of the key things is it's very rare to be able to do a remote sensing mission like this with the cameras and spectrometers that we design on the Earth, and then get a sample of this material back here and see if our observations, our remote sensing observations were correct. So that's one of the first goals. And we've already confirmed 4 key materials that were in the sample that we observed and we deduced were in the sample from the remote sensing data that are just from the quick look analysis that are present. The next thing is, does the sample contain organic compounds that could influence the origins of life? And yes, it's a very organic, rich, complex organic molecules and also water. So hydrated minerals, there's a lot of water molecules that are bound to the particles in here. So they really think, I didn't talk about this earlier, but one of the reasons Bennu was targeted is we think it's part of the earliest material from the formation of our solar system. It's the kinds of things that were delivered to the Earth during the early bombardment 4 billion years ago that delivered water and organic materials to the Earth. And so that is some of the hypotheses that are being tested by the scientists. What does this sample tell us about the history of the solar system and the Earth? And then has the sample changed since its collection? That's also very important to understand the context. So those are some of the big, there's 12 overarching questions that fit into these 4 categories. The sample analysis phase of the mission is 2 years. It's 2 years that is funded for a team of about 80 different institutions to do specific analyses that have been planned out over the last 10 years for the mission. This just shows you some of the institutions that are receiving the sample. The 3 major ones are Goddard, University of Arizona, and Johnson Space Center. Goddard is receiving one of the largest apportionments of the sample. It'll be in Building 34 in Jason Morgan's lab. This whole sample analysis program represents only 25% of the sample that's returned. The other 75% is being archived for future generations. So we like to say that our children and grandchildren who aren't even practicing scientists or engineers could write a proposal to NASA in the future to do some new study with the sample material, with a new technique, with a new instrument, or whatever. Very much the way that new investigations can be done with the Apollo samples today. These are just an example of some of the different institutions and studies that are going to be, facilities that are going to be brought to bear on the sample. And the other amazing thing about sample return is you're not confined to what you can pack into an instrument that can land on a rover on Mars or something like that. These, you can bring the sample back and use these world-class facilities to do analysis. It just wouldn't be possible with a spacecraft. So I was very lucky a couple of weeks ago to go to the Smithsonian. It was November 3rd when the sample that is on loan to the Smithsonian Natural History Museum was unveiled to the public for the first time. So this is a little bit of Bennu. This is the display case that it's in. If you want to know where it is, it's on the 2nd floor of the Natural History Museum, just to the left of where the diamond is. So nice spot there in the meteorites gallery. But really hard to put into words what it was like to put your nose up against that glass and be 6 inches away from this piece of asteroid material that's traveled 4 billion miles over the course of this mission. So close to home, and I encourage any of you to go take a look at it. So this mission, really a wonderful feather in Goddard's cap. When Goddard won this mission in 2011, there were some people in certain communities that were losing their mind that Goddard was going to be leading this planetary science deep space exploration mission. It's not the kind of mission that Goddard did. There were other centers that were supposed to get to do those kind of missions. And what we learned in the course of doing this is that there was nobody that was prepared to do this mission. We had to do a lot of things new. A lot of the navigation that I talked about, some of the capabilities. We just didn't understand what it was like to operate around a body that was this small. We really had to figure out some things for the first time to make that happen. And we did have some involvement from our colleagues at JPL in different phases of the mission, and they will tell you now, yeah, that was a very challenging mission, and we didn't have the capability to do it either with our legacy capabilities. So really wonderful that Goddard was the lead of this mission and got to be a part of such a wonderful success, a mission that was really model, stayed within time and within the original budget in spite of all the uncertainty and challenges that were confronted by the mission. So, thank you very much for your interest. I'd be happy to take some questions. And I also brought these little handouts which depict, it's a lenticular that depicts the tag sequence, the final 4 feet or so descending to the surface. So Lisa will help hand those out. And if you want to come up afterwards, one of my amazing colleagues had this 3D crystal made, and you've probably seen these where someone will have like a photograph that is put into 3D. Well, this is actually a digital terrain map of the tag site with the spacecraft hovering over. So it's purely authentic based on the modeling, the LiDAR data that we got from Bennu and everything. So I encourage you to take a look at that. It shows you the kind of scale of the moment, a few moments before touching the surface. So again, thanks for the opportunity to talk to you guys, and we're happy to take any questions.
I just want to say that we have lots of swag at the visitor center. So please, and I have a little pin on here on my lanyard. So please feel free to stop by. And we don't have this. This is great. Thank you.
Yeah, go ahead.
Yeah, this is an incredible mission. Like a large mission where you send 8 minutes, 17 seconds. This is an order of magnitude more terrifying. My question is, with all of these new procedures working so far away, and microgravity, how in the world did you test that?
Yeah, that's a great question. So it's always, I'll give a couple of examples, like all the optical navigation stuff that I talked about. Lockheed Martin created this like 30 by 40 foot wall in a facility, and they made it look like an asteroid surface, and they operated the camera systems and LiDAR systems against that surface. It's not the same. You know, the lighting is not the same as the sunlight. It's very challenging, but it does help you. You know, that was still helpful to us. We also did testing with the cameras, just looking at stars and looking at the moon and trying to get different scenarios that were challenging from that perspective. So we did individual tests like that. The actual collection mechanism, they actually had a test where it flew on the KC-135, the 0G parabolic flights, and they attempted the sample collection in that weightless environment or close to that new environment. That test, seemed like it was great, but we never saw in any of those tests a scenario that completely packed the head and jammed the flap open. So, Bennu, whatever it was about the material we collected at Bennu wasn't representative of any of the tests that we did. So, you're doing something that when you're going to some place like this, it's really truly exploration, and there were certain things we didn't know even until we touched the surface of Bennu. We were surprised still about how it would react. So. Sure.
Is 70 grams the total amount of tonnage material?
We think it's more like around 120, but because we haven't gotten the head open yet, so we don't have a great measurement of it yet. So that's
what are you expecting to get the head open, and how much are you expecting in
Well, like I said, I think the total is around 120,
With, once you get
well,
there?
based on the data we've got, but they're taking their time right now. They're focusing on getting the sample out to the teams, and you know, I'm not sure when they're going to go back to try to get into the rest of it ahead, because there's no
How
rush.
many institutions do you think about a grant or?
It's more complicated than that, because it depends on like their specific investigation and how much they need, and is it a destructive investigation, is it going to be returned, you know, like, so it's very, very complicated, but they're taking very, very great care, which is why we're like a month and a half into having the sample. We're still just like figuring out how to get it out of the head, so, yeah.
Yeah, if you hadn't had the density variations such that the down spread around, would that mean that you still have it closed and nobody could get samples right
The density variation, I'm not sure about.
now? No, I thought you said the samples that were distributed was from.
Oh, no, yeah. So we actually got quite a bit of sample just from when we flipped the head over.
But you haven't opened the main cabinet.
Yeah, so this, the sample that you see here, and then just by sticking tweezers in here, you can pull out a lot of material that's in the head. So that's the 70 grams they got, was just the easy pickings right there, but they think there's maybe twice that inside.
So would they have opened it sooner if they hadn't had that residue around and distributed?
No, not really. I mean, I think that slowed them down a little bit because they wanted to clean up all of that stuff before moving into the head, but they did that in maybe a week or so.
And so they haven't opened it yet?
So they have not opened, they haven't actually removed this piece, but they're, you know, they have 70 grams right now to work with, which is keeping them really busy, so.
You had this projected landing zone, this nice oval, and you had this small parachute malfunction. How close were you to not falling within that projected zone?
We actually were within the projected landing zone, pretty close to the west side. I mean, the east side of the ellipse. Back to that. We landed. The final ellipse we had was actually smaller than this. This was like the bounding ellipse that we had a month out. And as we got closer and closer, the predictions got smaller. So we ended up landing right about in this area, which was kind of, you know, outside of our predictions, maybe 8 miles from the center. But we think a large part of that is due to the atmosphere being thinner than what we expected, and that caused further downtrack. If the parachutes hadn't come out at all, the ellipse is actually smaller because a lot of the air comes in on that final descent on the main parachute when you can be blown around. The rest of it is just like all upper atmosphere stuff. So.
But you weren't prepared for it to land without parachute at all.
Well, the Genesis mission in the 2000s timeframe did have a hard landing. And so one of the things that we did was prepare very diligently. If we had a hard landing, what would we do? How would we respond? And because of the design of this capsule, with it being enclosed within the sample canister, we think that like some of that material that was on the deck that you saw may have been compromised, but all the stuff in the head would probably be fine. So our procedure was to basically get the hardware, get it into that clean room as quickly as possible, you know, as opposed to standing down and, you know, standing around looking at it in the soil. The idea was get it into the clean room and then begin your anomaly investigation of what went wrong. So, but luckily we didn't have to go down that route. Yeah.
How did you get to keep the thrusters from contaminating the sample?
Well, the sample canister is actually closed, the SRC for the whole mission until we were ready to stick the head in. And then the tag sand head itself was in a little enclosure stowed against the spacecraft until we did the tag of that. So there's some small possibility of contamination, but it was managed the best we could. Yeah.
Can you point out where in that ellipse the capsule actually hit?
Yeah, I don't know if this is the best view of it, probably, but it's basically right about here. But our revised landing area was a little bit smaller than this, so it was pretty close to the eastern edge of our final prediction.
Now, Mike, when we were writing the proposal on this thing, clearly one of the real tricks here is the navigation. And as I recall, we were proposing at one time to have 3 navigation activities running almost in parallel.
with Lockheed Martin, we had Kinetics, and we had Goddard. And the whole idea was you do a voting. If there's something's amiss, we do the best, best 2 out of 3. So I was wondering how that, first of all, was that ever implemented? And second of all, was that an ever out?
Yeah, so the primary navigation, all the innovation I talked about was done by Kinetics Aerospace. They led. And that's the trajectory determination, the maneuver planning, and the optical navigation. They had leads in each of those areas, really first-rate people. We also had a group at Goddard that was basically following along with them. So we had civil servants that were embedded with the Kinetics team, working hand-in-hand with them to do the navigation, but also using some of Goddard's own tools and doing it independently. And that wasn't just to have a check. It was because we wanted to be able to build up the capability within Goddard to do the same things that we could do with these Kinetics. The Kinetics could do with JPL legacy tools. We also had a JPL team that was following along for the shape modeling part of the mission, so a very specific part. They built their own shape model, and that was envisioned if that didn't work out and we had trouble with the shape model, we'd have another one to fall back on. And so all of that was like risk mitigation to make sure that we didn't get stuck with the navigation piece. But the Kinetics team working with Goddard was just really phenomenal, and just it took a lot of hand-in-hand work with the Lockheed Martin team that they weren't used to, like the thermal modeling I talked about. We had to get a lot of help from them to feed inputs into the nav models based on thermal, for example. So, but that's really an amazing accomplishment of the mission, all of that work. Great collaboration. Yeah.
What's your next challenging mission?
Well, this mission is not over yet. This is an interesting footnote. So right after the spacecraft dropped off the capsule, it did an Earth gravity assist, which took it into the inner solar system. So OSIRIS-REx spacecraft is headed to a solar flyby at 0.5 AU, so half the distance between the Earth and the Sun. It was only tested and designed to 0.72 AU. So we're taking the spacecraft to an area it was not designed to go. Lockheed Martin came up with a technique to keep the spacecraft, the most important parts of the spacecraft from getting too hot. It's called the fig leaf attitude. And it takes one of the solar rays and kind of puts it over the delicate parts. That's where the fig leaf comes from. But that's exactly what's going to happen. So there's going to be some things like the low-gain antenna is going to be sitting out there, and all the paint's going to boil off it. But the instruments and the batteries and the reaction wheels will all stay at a nice, safe temperature as long as we can maintain this attitude. So actually the team right now is getting ready to configure the spacecraft in this new attitude. It's getting close to that thermal limit. And then we'll go through that period, that trial by fire, if you will, in December and January. And if everything survives, then we're on to study a rendezvous with an asteroid called Apophis. And Apophis, we were selected to do an extended mission to Apophis. The rendezvous will be in 2029. And the reason why Apophis is an interesting target is because it's similar in size to Bennu, but it's going to fly by the Earth on April 13th of 2029 at an altitude of 30,000 kilometers. So that's lower than the geostationary satellites. And an object of that size flying by that close is like a once in 2,000 year occurrence. So like hasn't happened in recorded history kind of thing. OSIRIS-REx will arrive at the Earth an hour after Apophis. And that will allow OSIRIS-REx to get into the same plane as Apophis and then rendezvous and do a detailed study. And Apophis is flying by the Earth so closely that we think it's going to be reshapen and its spin is going to be changed. And so there'll be like landslides on the surface that we'll be able to detect by close-up imaging. We'll be able to see disturbed surface and things like that. So that's a really exciting mission, and it'll be really compelling because people will be really excited about this big object flying by the Earth. Our job right now is just to get OSIRIS-REx to survive 6 years past its design life in this very extreme environment to be able to do that mission. So we're pretty busy with that for the moment. So
the asteroid is off track, it might hit the jumping thing?
No, they have ruled out that Apophis is a risk to the Earth. Bennu is actually more hazardous to the Earth than Apophis. So. Bennu has a chance of 1 in 1,700 of impacting the Earth in 2180s. So. And the whole study that we did, 2 years of operations, it allowed us to refine that prediction and revise that uncertainty. Wait, so one more question?
Yeah, with Bennu, what you've learned now, is that reshape the risk analysis in terms of how risky Bennu would be if it actually intersected the Earth's atmosphere?
Yeah, for Bennu specifically, it helped us really get the error bars down on that estimate a lot. But it also helps just in general understanding, how those predictions changed, and now we can apply that to other hazardous objects. In fact, there's a meeting in Washington, D.C. this week of the planetary defense community, and they're talking about rendezvous missions to hazardous asteroids, and they have a bunch of Star Trek lessons learned kind of things that they're talking about.
Low the density of that is, would they think it would no longer be a threat, or would it still be a threat?
I think it would still be a threat, but the techniques they might use to mitigate that threat might be different based on their understanding of its properties now. It's basically a giant rock pile, and that would be different than a solid object. All right, well, thank you very much.